Today's section is section 10.1, properties of tangents. Our goal today is use properties of tangents to a circle. So our first definition we need to discuss is a circle. A circle is a collection of coplanar points that are all equidistant to a common center. Our next term is radius. It is a segment from the center to any point on the circle. And lastly, a diameter. It is the segment through the center with endpoints on the circle. And note the diameter equals 2 times the radius. There are 3 other terms we talk about with circles, and they are chord, secant, and tangent. So a chord is a segment with endpoints on the circle. So if we have a circle here, we draw any segment such that both ends are on the circle, we call it a chord. When we go back up here, a diameter compared to a chord is that a diameter is a chord through the center. Otherwise, we call it the longest chord. And just to finish off here, radius as well. Now, what's different? Secant is a line that intersects a circle twice. And the key being here that it is a line, first of all. And since it intersects the circle twice, it has to go through and beyond since it is a line as well. All right, our last term is tangent. A tangent intersects a circle once and is perpendicular to the radius at the intersection. So if I were to draw a radius on this circle, if I were to go perpendicular this would be a tangent line. While it looks like the tangent is close to intersecting the circle multiple times, it actually only intersects once. Given this diagram, name each type of segment. Notation is important. Alright, AB, the segment, right there, is the radius. EB with the arrows is a secant because it goes through the circle twice. CB is the segment that goes across the circle through the center, making it a diameter. DC if this is a right angle, that's also a right angle, meaning this is perpendicular at the point of intersection, making this a tangent, whether it's a segment or a line. Our last one is the segment EB, which stops on the circle, which makes it a chord. Our next topic is intersections of two coplanar circles. I have drawn here all the different ways that two circles can intersect. Option 1, 2 points of intersection. Option 2, 1 point of intersection. And option 3, no intersection or none. The reason we talk about these intersections is because they are often referred to with common tangents. And as we can see, a common tangent is a line that is tangent to both circles. We can have multiple circles. Our first option here, where we have 2 points of intersection, we also have 2 tangent lines. The next pair of circles, we have this common intersection point. That is also where our one and only tangent line is. Our next example has that same common tangent point, that point of intersection, but much like our first example, it also has these 2 on the outside for a grand total of 3. If you have one circle inside the other, that is called concentric circles, one inside the other. And they have no common tangents because there's no line that is tangent to both circles. On our last example, we have the 2 outside, which are referred to as external tangents. But we also have ones that go through the inside, referred to as internal. So these 2 circles have a total of 4 common tangents. Next example. Since a tangent is perpendicular to the circle, it forms right triangles. Our question here, is GH tangent to circle F? Or in other words, is angle G a right angle? How do we solve this? Again, we use the converse of the Pythagorean theorem. So we will say that 25 squared plus 60 squared, and compare it to 67 squared. If they're equal, it's a right angle. If it's not equal, it's not a right angle. Since we find that 67 squared is larger, it is obtuse. Is GH tangent to circle F? No, it is not tangent, because it does not form a right angle. These types of problems can be tricky. In circle I at right, J is the point of tangency. So what happens here is we have two radii involved. Since we know it is tangent, we know that is a right angle. So our short side is R, our longer leg is 48, and we know it's a right angle, so we know it's equal to. Now our entire hypotenuse is this whole thing, which is R plus 36 added together and then squared. We will square out on our left side. Now, this is the same as R plus 36 times R plus 36. And we will FOIL or distribute or box or however you multiply this. And get this. It is never R squared plus 36 squared. That is not acceptable and will be costing you several points. Now, we are going to get back to solving. I subtract R squared from both sides. And again, we are trying to solve for R. So we are going to subtract the 1296 as well. And we have 1008 equals 14R. Oh, sorry, 72R. Divide both sides by 72. And we got that R equals 14. No unit in this case, so that is all we would need to do. Common external tangents are congruent if they have a common external point. So they must intersect. If they do, then they have what's called a common tangent, and these are congruent. So x and x. So in our example here, we have 25 equals 6x minus 8. We add 8 to both sides and solve. And in this case, we do not have any units, so we would be done with this problem.